Welcome back. We are doing homework solutions for homework number 7 of a Thermodynamics 1 course. Problem number 3. So homework 7 is on entropy changes. Nothing really complex with entropy. We're not doing second law. We're not doing exergy or efficiencies or feasibility. We're just doing differences in entropy before we tackle those more complicated cases. Okay. So in this case, well, we have a real system. Okay. So we have a gas called Hadleyite, and it has a heat capacity of 3R. Okay? So Cp equals 3R. Okay? And it has an equation of state that says Z equals 1 plus Bp over RT, and B is equal to, where is it? AT. So AT is just a constant, okay? Well, I mean, A is just a constant, okay? And we're not going to worry about, like, what that constant exactly equals. We're just going to keep things kind of in relative variables, okay? So it's saying, assuming the total entropy of Hadleyite increases by this much, so we know N, okay, and we know the delta S, okay? The total delta S. So let's make sure that this is a big, nice big capital S. Okay. What is the final temperature if the pressure dropped from this to this and the temperature started here? So I've got P2 equals to something. I got P1 equals to something. Okay. And I also know where T1 is equal to. So I want to know, okay, what's the temperature drop for this system? Okay, so this is written in a just slightly different way, but it is a real system because it has an equation of state. Okay, so I have, delta S. We are going to assume that heat capacity is constant. Okay, there's not much else we can assume in this case. Okay, so we're going to have minus delta S departure. Okay, at T1 and P1, okay, because that's what we're given, plus delta S of an ideal gas, plus delta S departure of T2 and P2, okay. And we're going to draw our little diagram just to make sure we remember what path, okay, so we're going from here to here for our entropy. Things are going to change, and, it doesn't matter what pathway we take. So that could be the real pathway, but we're going to come down here to 0 and come back up. 0 because that's where the ideal gas is. Okay? And so, now, well, we're going to calculate delta S departure function. Okay? So that's from the ideal gas to real. Okay? And it's ds, well, what am I changing? That's right, I'm changing my pressure, but what am I keeping constant? I'm keeping constant my temperature. So this is dsdp at constant T, departure function dp. And we plug some things in, so ideal gas is 0, real is P. This becomes ds dp at constant T minus ds dp at constant T, but for an ideal gas, departure dp, sorry, not departure function. Okay, so ds dp at constant T is equal to minus dv dt at constant P. Okay? Same thing for the ideal gas one. Okay. And so we have to have our equation of state in terms of V, so Z is equal to PV over RT, and so what I'm left with is V equals RT over P plus B. And we'll just plug in B while we're at it, AT. Okay? So, dV dt, first off, our departure function is going to equal from 0 to P minus dV dt, constant P, minus a minus, which becomes a plus, dV dt, constant P of an ideal gas, dP. So dV dt, constant P, is going to equal just R over P plus A. And dV dt constant P of an ideal gas, where an ideal gas is equal to RT over P, well, that's going to equal R over P. Okay. And so when we look at this, it becomes minus R over P plus A minus R over P. Plus R over P, sorry. 0 to P. And these cancel out. Why? Well, that's the ideal gas contribution. So when we're doing a partial function, we're calculating the difference between the ideal gas and the real gas. Well, that's the ideal contribution according to this equation of state, and so those should cancel out. Okay. And so our delta S departure function is equal to, well, A is a constant, and so this just equals, AP from 0 to P, which is basically AP. Okay. Oh, a minus, because this is a plus over here, but this is a minus right here. So this actually is a minus. Okay. All right. Well, now I have to decide what I'm going to do with my delta S for an ideal gas. Okay. And so I'm going to erase this part. So I have two when it comes in an ideal gas. I have Cp over T dP minus natural log, R natural log of P2 over P1, or I have Cv over T, D1, D2, that should be a T, dt, plus R natural log V2 over V1. Okay, they are equivalent. Okay. But so I choose one that's going to give me, which is going to be easier, the one with volumes or the one with pressures. Well, I have pressure, so let's use this guy. Okay? And so my delta S total, or rather my molar delta S, is going to equal, okay, AP1 plus, now we're assuming constant heat capacity, so Cp natural log of T2 over T1 minus AP2. Now, I have a total delta S, so it's just going to be delta S divided by N. Okay, and so again, what am I solving for? I'm solving for what's the final temperature. Okay, and so I have this guy. Okay, so I have capital delta S divided by N plus A P2 minus P1, which is these two pieces. Oh, I forgot the minus R. Minus R natural log of P2 over P1. So plus R natural log of P2 over P1. Okay. Looks like I'm going to divide this by heat capacity. Then I'm going to take the exponential of the whole thing and then multiply by T1, and then that's my T2. Okay. So it's a pretty messy thing, when it's all said and done, but that is what it is. And at that point, I would just plug in numbers. Okay, and I think when you plug in numbers, you get the temperature to be about 350. Okay. So again, this really is, this is no different than any other departure function. The only thing that's kind of that feels different is that because of the lack of T that comes in here from, an enthalpy or a energy term, is that, those kind of things cancel out. Whereas here, things still kind of cancel out, but just not in the same exact way. So it's just a little bit different, but the mechanics of it isn't any different.